So passive microwave means it just measure the emissions directly, naturally occurring from the target rather than sending pulse or the energies to the target and reading the returning signals. And the emissions we can largely classify into four type of emissions. One is emissions reflected from the surface, and reflect means something like this, and emission emitted just directly emitting from the surface, and transmitted just transmit through the subsurface. Yeah, so reflect is like this, emission is like this in red, and transmit is just penetrate through, is, yeah, there's a transmit. um Something entering the subsurface. Yeah, and of course there's effect from the atmosphere, so we have to consider the emission from atmosphere as well. Because the wavelengths are so long, the energy available is quite small in case of L-band microwave, as compared to optical wavelengths and infrared wavelengths and C-band or X-band or Ku band of microwave wavelengths. So the field of view must be large enough to detect enough energy to record the same signal. So most passive microwave sensors are therefore, um, yeah, they show low spatial resolutions. So you can see that there is a soil and surface emission attenuated through the canopy and atmosphere. So we have to think about that. If you look at it here, yeah, think about that attenuation from the canopy and atmosphere. And there's downward atmospheric and cosmic background radiation, which has been indicated by BK. Where is it? Yeah, yeah, you have sky, atmospheric, and cosmic background factor, um, which will be attenuated through the layer, canopy layer, and atmosphere as well. And there's another emission upward from the upward layer, which would be canopy, which can be attenuated through the atmosphere as well. And there's a downward layer, which can be scattered at the surface and attenuated through the canopy layer and atmosphere as well. So as long as you can formulate this complicated scattering, I mean, like whether it is um, this is uh, whether it is reflected or just emission or like transmit, if as long as you can formulate it, then we can simulate brightness temperature. And in retrieval algorithms, they minimize cost function between the modeled brightness temperature and the instrument measured brightness temperature, and retrieve the physical parameters to minimize those differences. So this equation is just one model, just one example for tau and omega model, which is vegetation model. Um, so which would inquire soil effective temperature and emissivity, and some more information for nadir vegetation opacity and canopy temperature and vegetation single scattering albedo and we have to estimate the rough soil reflectivity. Then we can finally get brightness temperature, yeah, which will be attenuated by canopy temperature and atmospheric layers, and yeah, plus soil emissions. And then we can compare this model simulated brightness temperature with a satellite measured brightness temperature, and then we can pick um, soil moisture or daylight constant uh, that will reveal the minimum. I mean, that will reveal the smallest difference between the modeled brightness temperature and satellite measured brightness temperature. Um, so this is another example of another expression of tau omega model. As you can see in here, Ts is surface temperature, E sub S is soil emissivity, yeah, tau is vegetation opacity along the view path. Um, And this vegetation opacity means if the surface is covered by vegetation and soil moisture beneath the vegetation, their signal will be attenuated by the vegetation, right? So this term gonna consider that one. And then this vegetation opacity is a function of a vegetation water contents and incidence angle. And we will also consider some vegetation coefficients, which will uh, dependent on the vegetation type and the frequency. So the vegetation opacity is as a function of vegetation water contents. As long as we can reliably estimate vegetation opacity, and we may also be able to monitor vegetation water contents. This is the basic concept of this tau omega model. This is just one example. So based upon this retrieval algorithm, just cost minimization algorithms between the modeled brightness temperature and observed brightness temperature, we can we can find the dielectric constant values, which will be converted into the soil moisture as a function of soil texture. However, we can also retrieve soil moisture from active microwave sensors. This is just for a recap. There are various kinds of radars are available as active microwave sensors, and SAR is a type of a radar imaging sensors to scan an image 2 to 3 dimensional. However, scatterometer is non-imaging microwave sensors, like altimeter. It just measure a distance at the location right beneath the sensor. So it's not like having multi-angle like view, incidence angle, and so on. Just one linear dimension. And the SAR, basically just transmit a burst of electromagnetic energy and then read the returning signal, how much strong they are. In contrast, scatterometer sends pulses towards the surface of the sea or just surface, and then just measure the backscattered signal. Usually, yeah. Yes, and usually their spatial resolution is very low, just 10 kilometers or like 20 kilometers. However, SAR has very high spatial resolutions, about 1 meter sometimes, or like usually like 20 meters and so on. And there's strong radiometric variations, uh, and which can be applied for various kinds of environmental monitoring, like disaster management, like flooding or like earthquake, and precise in agriculture, wind, and so on. Because of that high sensitivity and strong radiometric variations, there's a speckle effect. Speckle is like just small spots, it's just noise. And so there are various tools available to remove, uh, yeah, and cope with the speckle effect. Um, so to obtain such a fine azimuth, azimuth means horizontal angle, horizontally, distributed angle. To obtain fine azimuth resolution, the physically large antenna is needed to focus the transmitted and received energy into a sharp beam with you know, high radiometric variations. The sharpness of the beam defines the azimuth resolutions. And the in contrast, scatterometer is widely applied for the estimation of wind speed or the turbulence of the ocean surface and direction and so on. And their precision is a tenth of decibel. So what do they measure? Like I briefly explained in the last session, the radiometers measure brightness temperature, right? And the active microwave sensors measure something like a backscattering. Um, Radar cross section is defined as a measure of energy that a radar target intercepts and scatters back towards the radar. So radar send a signal towards the target and then reading the reflected energy. So this relationship can be expressed like in here. It's a radar target distance square multiplied by the incidence power over the power scattered back by the target. And backscattering coefficient is just that relationship. Yeah, over the area, yeah, A, of illuminated surface over which the phase can be considered constant. So active microwave sensors measure this backscattering coefficient. However, the way that retrieved soil moisture can be varied depending on what type of sensors you're going to use. So if you were going to use scatterometers and change detection sensor, um, so in this approach, we will look at just relative difference between the backscattering in wet soils and the dry soils, and then we just measure the relative difference between the wet and dry, and then you can plug that surface soil degree of saturation to the soil water index profile, which is actually a function of characteristic time length t value. So if you look at the figures on the right hand side, t characteristic time t is kind of soil depths. Yep, yep. So this soil water index varies by the characteristic time. If you if you're going to change T values, and the SWI also will change. However, just a basic concept is that they are monitoring the relative evolution of the backscattering coefficients rather than try to estimate the absolute magnitude of soil moisture. Yep. Yep. And absolute, it is quite tricky and difficult to accurately estimate the absolute magnitude of soil moisture because that really depends on the incidence angle and polarizations and frequency and so on. So this is a very wise approach. Yeah. However, SAR, which is imaging sensor, for an example, Sentinel-1 can be considered as a synthetic aperture radar. So as compared to scatterometers, SAR shows a higher resolutions. It uses the motion of the radar antenna over a target regions to create images. And the water cloud backscattering model can be one option to use backscattering, SAR measured backscattering to retrieve soil moisture. Dielectric horizontal cloud of identical water droplets comprising the vegetation canopy are distributed uniformly throughout the vegetation canopy. This is assumptions when you are using water cloud backscattering model. And it also assumes there's only there's only single scattering is available and neglecting multiple and volume scattering taking place between the crop and underlying soil and within the crop. Yeah, so they assume that at C-band the double scattering mechanism has a negligible impact, especially in the case of the thin canopy structure like wheat. Yeah. However, this is not always the case when even corn and wheat, there may be a very complicated multiple scattering and the volumetric scattering arising from vegetations. It would be perfect if this can be accounted for. And third, the cloud density is assumed proportional to the water contents, per the unit volume of the canopy. And backscattering contribution from soil is modeled from the bare field locations for the shake-up simplifications. Yeah. So likewise, like all other models, this is another simplification for this model. So how it looks, how does it look like? It's like this. This is just one example of water cloud model to be used for the retrieval of soil moisture. The reason that I'm showing this one is usually this kind of approach require lots of coefficients to be calibrated in the field, like VV and AB, CD, and so on. And then you can finally estimate volumetric soil moisture. Volumetric soil moisture here. Yeah, volumetric soil moisture here. Yeah, from backscattering. of the soil. Um, so the limitation of this kind of approach is that it is extremely difficult to upscale to a larger scale because you don't know all these coefficients. So when you apply this approach, it is very important to check whether your study domain is uniform so that you can expand it to adjacent areas. And second, if it is not, if it is non-homogeneous, then it's better not to use this kind of approach. Yeah. So whether your study domain is small or large really determines what kind of approach or model to be chosen. However, this is one of the widely used approach, very traditional. The another way to estimate soil moisture is just use a physically based surface scattering model. And this is empirical model. You just go out to the field and measure several coefficients to be calibrated and then use the relationship that you get empirically. However, this is physically based model. So instead of using calibrated coefficients, you are going to use something like, for example, inversion or something like that. So like small sense map retrieval algorithm, which uses cost minimization of cost function between the modeled brightness temperature and observed brightness temperature. This approach also uses cost minimization between the surface scattering modeled backscattering, uh, also called integral equation model, and the satellite SAR observed backscattering coefficient. So this kind of surface scattering model also assume similar assumptions, like this, neglecting multiple, like this. Yeah, this kind of surface scattering model does not consider the volumetric scattering arising from vegetation. Within the vegetation and between the vegetation and then the soil underneath the vegetation. This is uh, the based upon the Kirchhoff and some Fourier transform of surface correlation function, which this equation basically just simulates backscatter using the input of surface information in more detail, like surface correlation function or RMS height. Yeah, characterized by RMS height and correlation function, and some instrumental configurations like what kind of polarization you're using and incidence angles and view angle and so on. And then you can pretty much characterize you can pretty much define these equations so that you can finally, if you plug in those informations into this formula, and then you can estimate backscattering, and then you will compare this backscattering with satellite measured backscattering, and then measure the differences. And when you can minimize those differences, and then you will finally find roughness conditions and dielectric conditions. They will reveal the minimum difference between the modeled and satellite measured backscattering. And then that directly constant will be converted into soil moisture when you define soil texture. So this is just one example. Um, uh, you can apply this approach for. So main difference is that you can see that you can estimate, large, uh, you know, watershed scale. You can estimate soil moisture at watershed scale as compared to previous approach in here. In this, water cloud backscattering model, you have to calibrate all these parameters at a small scale or a local scale or something that, small scale that you can carry out calibration and validation. However, if using this approach, you can estimate soil moisture at watershed scale, so that's actually one of the merits. Um, however, however, um, still there's uncertainty and retrieval errors. You were going to estimate roughness and soil moisture out of this retrieval algorithms, but it's like we discussed it before. This is ill-posed problem. So um, uh, there are many things that we actually should consider. For example, like vegetation cover. When your study domain is bare soil, it's relatively simple and easier. However, when you apply active microwave sensors to vegetative um, areas like agricultural lands, and vegetation is huge error source. So if you look at in this figure, the blue line is field measurement, and red is rainfall, and the dashed line is SMAP soil moisture that we can download from the website, and the just black line with a triangle is radar set 2 that we can retrieve from active microwave sensors. And before doing any bias correction, there's a large deviation from the field measurement. Looks like it's quite, noisy and fluctuating. And however, after the bias correction, bias and RMSE has been dramatically reduced. Even sometimes much better than SMAP soil moisture, as you can see in this table. So we have approached our approach. We have attempted some stochastic retrievers, considering uncertainty of retriever errors. Retriever algorithms, and then we could reduce the retriever errors very effectively. So if you look at this figure, you can see that soil moisture estimation in A and soil moisture estimates in C is actually a little bit different. There's a large underestimation in C, SMAP soil moisture. Um, 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 However, after carrying out bias correction for a radar set, we could better predict um, watershed discharge. If you see figure A, that is radar set bias corrected. B is SMAP, just download that we just download from the website, and we could see that bias corrected radar set correctly warned about the peak, the increase, sudden increase of water level before actually we see such a peak at the watershed outlet, right? So there is some like time lag, but obviously yeah, before the watershed outlet, we could pretty much predict there will be increase of water level just simply by looking at the soil moisture distribution before reaching the water outlet. On the other hand, if you look at the figure B, because of some underestimations we could see in the previous slides, they could predict increase of water level for the peak 3. However, for the other peaks, yeah, there was no successful prediction in advance. So this kind of retrieval errors may mislead warning and several warnings and predictions and so on. So the bottom line of this figure is that bias correction and reliable estimation of SAR is very important for us to properly use it. Yeah. As long as we can do that, we can pretty much just use this satellite of soil moisture just for forecasting flooding and many others, just without really involving any model calibrations and so on. So all the soil moisture that we have seen so far is all about surface soil moisture. However, as long as you can reliably retrieve surface soil moisture at 5 centimeters, usually when we say satellite, usually they cover top layers at several centimeters, we can actually apply the surface soil moisture, surface heterogeneity of soil moisture to land surface model, and then we can infer root zone soil moisture at 1 or 2 meter in depth. So there's a soil moisture profile. So surface soil moisture wouldn't be the same with the root zone soil moisture. However, we can do that through land surface model. And root zone soil moisture is actually very important than surface soil moisture when we want to apply the soil moisture for wildfire spread, because if the root zone soil moisture is getting dry, that means forests and trees can't make efficient evapotranspiration, and that means the fuel moisture will drop and fuel availability will increase. So root zone soil moisture is very important parameter for the predictions of wildfire spread. However, practically, I could see quite often that data is not available for vegetated pixel. So if the study area is vegetated, sometimes data provider just using their masking, yeah, the pixels are sometimes just empty and no data is available. So yeah, root zone soil moisture is quite important, but sometimes data are not available or sometimes contaminated by other uncertainty in the model simulations and so on. If applying soil moisture for wildfires, it is found that soil moisture If the soil moisture is very low and in dry soils, we could see that there were several lightning events to trigger more and more wildfires. So in figure B, the lightning is shown by yellow dot, and in figure A, low soil moisture is shown by yellow green. There was some spatial correlations. Um, about the relationship between the dry surface and dry lightning, we're going to talk about that in next session. How the warmed and dry land surface can trigger even lightning and storm and so on. And this is another example how soil moisture can be applied for the better prediction of wildfire. When there's this FAU stands for available fraction of available water capacity. So after drought conditions, I'm sorry, at low FAW, low fraction of available water capacity, there were drought condition and extreme conditions, and wildfire has been largely increased about 60 or 80, right? So most fires occurred at very low FAW, fraction of available water capacity, um, and some occurring under severe drought and most occurring under extreme drought at a very low, extremely low FAW. So you can see that there's a lack of water and moisture, and there will be more and more fire occurrence. This is kind of the relationship that we would like to show. We just briefly review how we can retrieve soil moisture from active and passive microwave sensors, and how we can relate soil moisture with wildfires. And despite the significance and the needs, soil moisture products are still vulnerable to vegetation errors. You know, we are particularly interested in vegetation because vegetation is actually play a role of fuels, in fire events. So we just keep talking about the vegetation things and vegetation errors. So because of this, uh, bias correction is very important because the limitation of a active microwave sensor is that their physically based model does not really consider vegetative land. However, for to apply this SAR for the fire expressed, we need soil moisture in vegetative land. So that factor, that vegetation error should be considered, and we just demonstrated one example when we use stochastic bias corrections, and then we could significantly reduce the retrieval errors from a SAR. And although SAR has a higher resolution as compared to scatterometer, passive microwave, and so on, they are susceptible to surface roughness, which is not explicitly formulated and often ill-posed problem. So ill-posed problem means although the pixel is very bright, we don't know whether that is because of surface roughness or soil moisture or vegetation structure or even topography. So SAR is very sensitive to surface roughness, as compared to passive microwave. It is the very tricky, yeah, challenging part in retrieval algorithm. Yeah, if we want to enhance the retrieval accuracy. And then next, although L-band passive microwaves better penetrate through the vegetation layers, their low resolution may contain some water body. Yeah, because of their longer wavelengths as compared to visible or optical sensors, their energy is so weak, so their resolution is very low, right? Yeah, so within their pixel, sometimes water body can be included, then that will affect soil moisture or vegetation moisture contents, right? Yeah. However, that is the case for the small water body, usually like something like a river case, like a river scale. Usually, retrieval algorithm using the masking, they get rid of the data over that water body pixel. So, yeah, yeah, so for the large water body, definitely it will not affect the pixel, but for the small scale water body, yeah, that may be included the pixel and will contribute to the overestimation. Finally, root zone soil moisture is very important for monitoring pure moisture. Yeah, low root zone soil moisture will induce low fuel moisture. However, sometimes the pixel is not available. Yeah, for the vegetative, highly vegetated pixels, or when there's RFI, yeah, radio frequency interference, or when there's a fire, yeah, and then data are not available.